technical stuff. So when I talk about the linear dependence, I say that there are some vectors within the set of the vector you have, which I call it VK here. You can write it as the linear combinations of all the other vectors, right? So I forgot to put the negative sign here, okay, just to clarify it, okay. And yeah, as you can see that I overmiss a lot of stuff. So if you find something really weird, so please come to me, and like it is likely I made a mistake, okay. Right, right, that's it. And also, like during the break, like I have some good questions. I think it would be good to point out here. So it's like I said that when you try to find the basis of vectors, okay, we says that let me. Is basis of V. Okay, no, you V twice. That's not good. V, and we'll call it W. Okay, and we want to show that the span of V equals to the whole space here. So someone comes to me and says that how can I show it? Like, so to put in the more simplest setup is like, now says that this W is R2, which is the XY plane that you are very familiar with. Okay, here. And the basis, what is the candidate of the basis, which can be like 1, 0, we call it V1, and V2 is 0, 1. Okay. Okay. So how can we show this? So you can say that for all x, y in this space, I can construct it with the linear combinations of V1, which is 1, 0 here, plus A2 here, to get whatever elements in the space. Okay, so if you can show it, then you are done. Okay. Right. Okay, so let's continue. Dot product. Okay, so this is the definition of dot product. So we have two vectors, u and v here, and it's you just multiplied each coordinate and then sum them up. Okay, so that is how you calculate the dot products here. And of course, like it has several property. For example, like the order doesn't matter here. Okay, and you can distribute the one vectors to the other one within the parentheses, and also like the orders you multiplied doesn't matter here. And what else? Yeah, so if you multiply it by yourself, then it has to be non-negative, right? And remember that we talk about the when we talk about the distance functions, we talk about the Euclidean distance, which is Euclidean known here. You can also use dot product to calculate it. In that sense, you are measures the length of your vectors u. Okay, so it's like you multiply by yourself and then take the square root of it. Right. And alternatively, you can also calculate the inner product in the following way, which is you put the length, like you multiply the length of these two vectors and more than that, you also multiply by the cosine of the angles between these two vectors. Okay, so I want to show like why that would be the case. Okay, so here's the proof. So first we are going to start from the law of cosine here, which you may already know it, but let me show you very quick. Yeah, so for any triangle here, you can draw a vertical line on the side of B and use the theorem to calculate the opposite side, which is C here. Okay, so first is the D squared plus E squared, and because you don't know what exactly number that is, so you use the sine and cosine to help you to find it. And then the trick is that you know these two add up when the when the sine, the square, how to say that, the square of sine and cosine add together, that will become 1, and that's the trick, and you prove it here. And then